Okay, I have a few little questions for you. My name is Rafał Pilarczyk, and firstly, I would like to ask you, how do you feel today? What do you think about the conference? Do you enjoy? Okay. I hope I will follow your view. And I have also one more question. Who is involved in machine learning? Please raise your hand. Machine learning. Who knows what is machine learning and how to use it? And who want to learn how to use machine learning? Okay, we have many hands. And who is interested in computer vision? Okay, a few hands. Okay, that's all. So welcome on my presentation about music generation techniques. And I am thinking about this, and I will show you some key points, okay, and my agenda. And firstly, music is also data, so I will try to show you my point of view on this data, especially data representation. This is very important in machine learning. Data representation is first point of, and data knowledge about this data is the first point of each machine learning or deep learning algorithm. Next, I will describe how we can generate music using different models and different techniques. And next, I will go to the architectures. Don't worry, you don't need to be Superman or Iron Man of deep learning to understand all these things. It will be very quick review of different architectures. Of course, I will try to convince you to study them by yourself. So I will not follow each model and describe end to end. There are many papers, really. It is very big topic. So it will be very quick, so stay focused. And next, some practical approach. Because I'm working in Samsung R&D Poland, we are doing machine learning from the practical point of view. So, short example, deep learning for vacuum cleaners, deep learning for fridges. No problem. Of course, it is a big problem, but you know, deep learning, practical approach, electrical engineering, many things. This is very hard, and it is not only Keras and TensorFlow and MXNet. It is something more. Okay, so I will show you some tricks, some things where you can start searching not only deep learning techniques for music generation, but also different things connected with this. Limits, future, and conclusions, of course, because models have many limits, and the possibilities which they give us are also very narrow for now. But state-of-the-art methods are doing a good job. So I will tell how we can improve some things. So maybe one of you can, in next 3 years, develop something incredible and become new Jimi Hendrix of artificial neural networks. Okay. So, very philosophical question: why do we like music? Anybody knows this question? Knows how to answer this? Why do you like music?
Because it affects our emotions.
Yes. What's more? What do you think? Do you like concerts? Performances? What music do you listen? Jazz, pop, rock, heavy metal? I am very big fan of heavy metal, so... so Chopin and Mozart and Bach. Bach. Bach was his work was very impressive on music, especially music from the I can explain this like science of music, because his methods and rules are seen nowadays. So Bach was first, and everyone is following Bach rules. So this is very popular formula. So why do we need AI for music generation? There are AI, of course, is a very hot topic nowadays. So we have AI in art. We have style transfer. I will show you some examples of style transfer. Probably you used Snapchat or Facebook camera application, and there are quite interesting filters. So it's style transfer. We can put style on one image using another. Generating images, videos, text. So we can generate new novel, new poetry, and this is of course connected with music. Novel, poems, and books, and especially natural language processing. And anthropomorphization of AI. So everyone knows this topic when we call AI is we can create something similar to Terminator. Yes, you know Skynet. Skynet was artificial intelligence which wanted to destroy humanity. So, short question: should we try to make AI more human? Don't know how to answer for this question. Okay. Science. Data science, the sexiest job of 21st century. Who is convinced to say that? And of course, fun, visible results. So on music generation techniques, on image recognition, you saw many presentations probably. We can get very fast visible results of, I can say, practical approach. So it's not only a piece of code. It's a piece of code which can produce something which is very pleasant for me. And of course, business part of AI music generation. Yeah, you can Google this name, Tyrone Southern, and he created her album using artificial intelligence, and the title is I Am AI. Of course, it is something. I think it is not created music using AI. It's probably a commercial approach to become more popular. But you can find this album and listen to this. And I don't think artificial intelligence can create such great performance. Bit about history, very quick. So ELIAC, it was first computer for which created music, and this track of ELIAC computer, this soundtrack can be found on YouTube. So you can Google ELIAC string quartet. And you see it was 60 years ago, and there is big gap between 1956 and nowadays. Of course, it's celiac computer, and Marvin Minsky. You know this guy, Marvin Minsky. Very popular man. He's winner of Turing Award. He's co-founder of MIT AI Lab, and he wrote some I don't know, some words, some piece of information about artificial intelligence and of course music. And he tried to explain music from the AI part. And in this paper we can see the conception of agents. So basically we have many agents, and one agent is understanding that we are playing drums, bam, 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 bam. Second agent is understanding that we are playing guitar and following chord progression. And that's all. This. Sorry, I will share you this presentation probably. Music, mind, meaning. Music, mind, and meaning. You can Google it. It's quite a big paper about AI in music. So let's get started from data understanding. So I will try to show you many data types that are used in deep learning techniques for music generation. You know, Fourier transform of signals. So when we are listening music, we are listening something like that. And of course, Fourier transform is representation of signal, but we want to know how to, using this, yes, Fourier transform, create something that can be pleasant for us. So we want to become AI rockstar. And songs are created, this is probably not song, it's speech, but you can see that there are many fragments. Probably there are one word, there is one word. So in music, on spectrum, we can see that there are many parts of music. So when guitar is playing, our spectrum is different than drums, etc. And music from the composer side is of course created of some parts. So we have melody, main melody, la 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 la. We have main theme, and this main theme is probably the most important part of this song. When you are singing during the shower, you are singing something popular from advertisements or from your music from your favorite artists. So there is a basic theme, there is a melody, there is harmony, key, meter, rhythm, dynamics, texture, form, many things. And how to catch all these things? We are data scientists. Probably there are not many data scientists who are musicians. And it is very difficult to join these two things. So I will try to explain firstly something about this. Maybe some people right here played the piano, played the guitar. They know some rules about music, but probably there are many people that don't understand how to create great song and what is meter. Probably meter is very easy term, of course, but there are also texture, form. How can I catch these things? And song structure, of course. Czyli we have song structure, we have intro, chorus, etc. And what instruments do we want to use? So melody is a series of pitches, notes, to create some kind of pattern, and each element has own length. Additional characteristics, and we don't worry about this. Melody can be smooth, easy to play, or difficult to play, and it depends on the pitches in melody, and melody can be main theme. A melody can be also played in scale. Scale is something more generous, but we try to not follow these rules for now. Okay, so this is one note is higher, one note is higher than another, and that's all. Okay, you have any questions? I am not a musician, so you can have many questions about music, data representation, etc. Okay, so harmony pitches combined vertically. Probably many of you saw these things about hordes. Who played Knocking on Heaven's Door on guitar? You like this song, Knocking on Heaven's Door? Yes. And probably you, if you don't play guitar recently, I can bring you guitar, and you can and you remember what chords you used. So it's chord progression for chords, and this is one chord created from 3 notes vertically. That's all. Meter, czyli regularly recurring beats. So I am drummer. I am drummer, heavy metal drummer. I played on my studies, and drums were very interesting instrument for me because it was very simple. I am using my drumsticks and playing some music. A meter is it's very simple thing because we have regularly recurring beats. So when we are counting to 3, 1 and 2 and 3, and we have triple. Yes. Okay, and of course tempo. Tempo is also very important in music because we are using deep learning techniques and we want to apply tempo into our model. Okay, it's triple actually. So we have 3 notes, 1 and 2 and 3 and okay, that's all. Dynamics, so we can play something quiet or noise, texture, a number of melodies in relationship, polyphonic and monophonic. So when mobile devices 15 or 12 years ago was having a big impact on our lives, there were monophonic and polyphonic ringtones. So probably you could remember this. Style, it is very important from the music part because we need to know we can mix classical music with rock music in our data set to create something. So this is a simple TSNE plot about styles. So we used features, some kind of features to describe what style of music is this. So after TSNE, yeah, you know this algorithm, TSNE? It is algorithm for data visualization, similar to PCA. Of course, it can be used in different things, but for data visualization, it is quite good. And we can use features. For example, we have vector length of 20 or 30 or 50, and we want to divide into parts. So we use TSNE to divide into parts and check what are the relationship between this style.
What is on which axis on the picture?
Sorry, could you?
What is on which axis? I mean, this number.
Axis. It is okay. So in TSNE, it doesn't matter actually the axis. because it's important to visualize something. So it is not it is actually feature length, but it's feature length after TSNE algorithm. Okay, so it's actually iterative algorithm on changing data representation from 20 to 300 dimensions into 2 dimensions. Okay. Data understanding song structure. So we have many song structures. We have intro, main melody, which are at the start of our song. We had verse, chorus, bridge, breakdown, outro, and this part of song should be considered during data representation, because we can use song end to end, so from verse to chorus and the end of our song, but probably our algorithm, our machine learning system cannot distinguish these long-term sequences. So probably it could be a great option to divide our song into these parts. Of course, it's difficult because when we download our song, it is not divided into parts, into song structure, into elements. So data scientists need to do it manually, probably. Okay, that's all about song structure. And this is style transfer. I want to show you at the end of data representation. So we have a nice picture painted. I don't know who painted this. We add to this this picture of Samsung S8. It's not advertisement, sorry. It could be everything. It could be our face, whatever. And our style transfer algorithm is doing something like this. So we have mixture of these 2 elements, but it's not filter. It is not Photoshop. So we don't put 2 consecutive images, one at the top of another. It's something more semantic. So we can see that mobile phone here have different texture than the end of the scene. So it's semantic style transfer. It's very also hot topic nowadays. And we can say that it is an art or not. It is created using algorithms and using computing power, using our GPU, because this algorithm is very demanding. So could be this an art. Actually, using current definition of art, it cannot be called art because we have human. So humanizing artificial intelligence, I don't know, it's good idea from this part, because actually when we put these 2 images, each time generated image can be the same. Of course, we can add some noise and extinguish between 2 results. But DeepHear.io, you can when you are using a mobile phone, you can search DeepHear.io. You can upload your photo and create style transferred image. Okay, and we started from data representation. So now I will describe our data set. Our data set is not only signal, waveform. Okay, so we have our wave. It's our music downloaded. It's our Lady Gaga, and it's Fourier transform result. And you know it's difficult to analyze this and use this waveform to create new music. Data set probably quite big. One file size is about 6 or 10 megabytes. And I will tell you, I can tell you that songs and artificial music created using datasets such like this is quite noisy, because we are using different representation and then we want to create something similar. You have two big things about using waveform as a data to create and generate music: Magenta and Synth, and WaveNet by Google DeepMind. Okay, and you can see this is the original waveform of this music, and this is music representation created using artificial intelligence. So it followed the rules, you can see, but it is compressed. So our compressed version of this file size is different. Probably you learned something about compression, about standards, about I don't know how to say that. Anyway, this is compressed signal, and of course it is quite noisy. No, we can't pack all these things into a vector representation. So we have MIDI. MIDI is quite interesting data representation. MIDI is not rarely used. It is used, for example, in keyboards. So using MIDI, we can create maybe not pitches from MIDI to pitches, but we can create something which can be representative for music. So we have some kind of events and messages. We have messages that hold pitch, velocity, control signals. And main idea about this MIDI is that the events are about nodes. So we have node on and node off events. So we can play or not play. It's quite simple. So we will use probably 1-0 encoding for this. Node on is 1, node off is 0. Okay, so for example, node on 265.55, on channel 3 because we are counting from 0. I'm not counting from round 1. On channel 3 we started playing F4 with velocity 55. And that's all about MIDI, but it's very difficult to parse MIDI for your data set. So probably I will show you some tools to create this more pleasant and faster. Okay, so this is MIDI and with piano, and we have frequency of notes. We have MIDI number and note number, and this is something which can be parsed and used in different kind. Okay, piano roll is quite nice representation. It's very popular. So we have piano, and for each piano key we have one line. So for 100, for 20, I don't know, 120. Anyway, we have our piano. So for each key we have line. You know, this picture presents automatic piano. It's very old invention. So we put this tape in our piano, and piano was playing something using this holes. So this hole represents that we are putting our finger on this key. It is of course, it is used for piano, not for guitar. Probably for guitar we cannot see this representation because there are better representation. ABC notation. There are also many data sets about ABC notation. So it's representation of music using some letters. Okay, chords. So we have chord. We have one root node, one type, and usually in datasets it is used in jazz music. And I will show you something about chords. You know word-to-vec embedding for natural language processing task or not? Who knows what is word-to-vec? Okay. So word-to-vec was idea to create from vector representation one hot encoded words into continuous space representation. So we have 1 and 1, 0, 0, 0, 0, 0, and we want to create from this representation of word. For example, it can be cat. Cat representation is 1 and many zeros. And this is first word of our dictionary. And we want to create from this thing something from the continuous space. So we don't want to use 1 and zeros, we want to use floating numbers. So word-to-vec is something similar. So instead using E7 as a vector of 1 and zeros, we want to use continuous space to build our models, and it is called, of course, embedding. When you type keras embedding, embedding is something like this. And about word-to-vec, okay, and this is very good thing about word-to-vec, because creating embeddings in natural language processing started from embedding. We can see that semantically this walking and walked and distance between these 2 points, so it's distance L2 or norm 2 or norm 1 is the same as swimming and swam. So it's past form of our words. And we can create something like adding these vectors. So when we have men and women, and when we add this vector of women minus men to king, we can create new vector in this space, and it will be queen. So you know, you feel this. King minus queen is the same as man minus woman. Of course, it's not the same, but the length of this vector is similar. And this is word-to-vec, and this is maybe you know what it is. It's circle of fifths, and from music theory, circle of fifths is good point to start learning how to play music and create something pleasant. So we have E, G, and this major and minor keys are related to each other. So when we created this embedding, word-to-vec, but for chords, we can see the same relationship. So between E and G is here. We can see that it is the distance between these 2 chords is in a relationship. It's quite close. And I want to say that how this happened. Our artificial intelligence, our machine learning, created something which is called circle of fifths, and we can try to draw this circles, and it works. How this happened? I have 2 explanations. Artificial intelligence is not as good as we think, and it is not the strength of our algorithm. So it created new rules from dataset. You know, dataset is biased. you know this word, biased. I mean, every song in this data set was created using probably this rule, so rule of circle of fifth. And that's why this happened. So we discovered this. But it is not the thing that describes that artificial neural network or different kind of artificial intelligence is impressive intelligent. Okay. Lead sheet. Lead sheet is about specifies the essential elements of songs, so melody, lyrics, and harmony. Big database, LSTM, flow machines, com. And actually, when you Google flow machines, you can see many things related to music generation techniques. Also many papers, so I really appreciate their work, because their work is quite impressive. So this is lead sheet. We have melody, harmony, and lyrics. Okay. Rhythm. So quick view on this. So we have percussion. We can play on the instrument or not, and this is quite simple data to use. Okay. That's all about data representation. Sorry for this, but data representation, I am practitioner, so when I'm creating something like artificial intelligence for music generation, I am doing it not for research, but because we want to put this in some kind of product. But data representation is very important in this, but you know, natural language processing tasks. So we have words. Words are easy to understand. We can read about something and we understand this. But music has, as you see, many aspects we should consider before creating something. So this is very difficult to contain music rules and music knowledge combined with data scientists, deep learning, machine learning. So how to explain time in our algorithm? So we have two rules. I didn't see any rules that I could add here. So we have global time, and it is fixed. Fixed, and architecture is for not recurrent architectures. And time step. Time step is the easiest. So we use some kind of atomic granularity of our node. So the 16th node is our time step, and we were using this for time explanation in our algorithms. Input encoding, of course, 1 hot on value from 0 to 1. One value from 0 to 1 probably should be after hard embedding or something like this. So we have to create new continuous space for our data. Transposition of data. So we have song. Song is created from pitches, melody, I don't know, and we transpose it. So play from the end to the beginning. And it is, this rule is used for kind of sparsity in more generic examples, and it is trick. It's not proof that would always work, but it's kind of trick which can be included in this. Okay, so one hot encoding, we have a vector, and one is our node here. This one is our node here. So these vectors are following the rules that of time step. So each vector is for one time step. Okay. So let's begin about the meat of this presentation, about architectures, about practical approach, about possibilities. what do you think about deep learning? What do you think? Who think that deep learning is import keras? Who think that he's I don't know, Jan LeCun? Who think that he's a dog and putting something to recognize image? What society thinks? So Terminator. What my friends thinks I do. Probably brain connected with I don't know, digital signal processor or something. What other computer scientists think I do? You know this picture from Breaking Bad, this man landing on this big amount of money. Okay. So first the generation process. So we want to create our model, but we want to generate something. So we have few approaches. First approach is feed-forward, so used for feed-forward neural networks. It can be autoencoder. I will describe autoencoder later and how to generate this. Sampling. Sampling is a very, very common rule of generation music from a model which follows kind of distribution over data set. So Gibbs sampling, Metropolis Hastings, also Monte Carlo Markov chain sampling with pseudo Gibbs sampling. So there are many algorithms to create music, and it is very, very simple algorithm. I will not explain how to use this and put some nice LaTeX notations here. Input manipulation. So Deep Dream, DeepHear, similar things. We have our neural network, so we are manipulating neurons to create something new, and it's input manipulation. In Deep Dream, manipulating neurons can create something very strange, and these images are very strange. You can search Deep Dream if you didn't. Adversarial, reinforcement, unit selection. So we have this adversarial and reinforcement, I will also describe later, but unit selection is a quite interesting method. So we have data set not created from single nodes, but created from fixed length or not fixed length part of song. So 3 second parts of song can be concatenated. So we have nice guitar, yes, 1, 2, 3, 4, and that's all. And this is our one sample in our data set. So later, we try to figure out how to take all these short song elements to create something bigger. So we concatenate them.
Excuse me? And have you tried any of these methods?
So,
have you tried any?
Yeah, I tried feed-forward, sampling, input manipulation. DeepHear is very old method, so I didn't try this. Adversarial, of course, reinforcement.
So you're taking pieces of the other music to create your piece of music. It's legal.
I will explain this. You know, very weak point of artificial intelligence for music generation is data set, because there are many data sets. We can use Bach, Mozart, Chopin, so probably most of the results that I want to show you today are created using this public data sets. It's a big problem. When we want to create new Lady Gaga, it is illegal to use her song to create something like this. And who has rights to this song created? In our country, the possession of song is undefined. So artificial intelligence created song in our country couldn't be sold because we don't have rights to do this. Okay. So, multi-layer neural networks, and these architectures that I will try to show you is very quick review about all these things. So I don't put all these details about this. So I convince you to search and find how it was created. So some keywords were put it here. You can follow them after the presentation if you are curious. Predicting next element of sequence. This is the task that I want to use. So we put some song elements as our input, and we want to predict what should be next pitch of our music, next hold. It's predicting. We are predicting our music in the future, and after predicting, we are adding this and use for new prediction, etc., etc. We can add some condition. So for each part of our song, we can add bass structure, beat structure to enforce our neural network to follow the rhythm. Okay, it's very difficult to create something pleasant using all these architectures, and many tricks were included in all these things to create something similar to things that we hear. So it's quite simple, iterative, multi-layer neural network. And our seed is here. We are putting some vector and predicting what should be next. Okay, DeepHear as an example. So it was a piano roll used to us. That's why I included this in my presentation. One-hot encoding. Time quantization, 16th note. So 16th note is our time granularity. Vocabulary, about 80 note. You know, vocabulary in our languages, I don't know, 20, 30 letters, yes? Vocabulary in music is much bigger. Except this all 80 notes, we have also some kind of additions for our song. So we can try to play something louder and louder, and these things happen in music, and it's easy to understand but difficult to include in our data as a vector. So it's Autoencoder. Random data as sit in bottleneck layer. So we have something like this. Here's our input for training. Okay. And this layer, 16 neurons. So we are compressing something. As an input, we have 5,000 bits. So 5,000 vector of 0 and 1s. And we want to compress this into 16. Vector 16 length. And after this, we want to decompress this. So decode our from this latent layer, hidden layer, we want to reconstruct this. So the task is very easy to understand. So we want to, from our input, we want to generate the same. So we want to encode this into this layer with 16 neurons and decode into the same length vector. And one more thing, when we want to generate music, we can use this hidden layer, because in this training process for deconstruction, reconstruction, autoencoder, so it's encoding, decoding, this hidden layer is very well trained to hold whole information about our music. So manipulating this thing, putting in this hidden layer pseudo noise vectors, we can generate some kind of music as an output. So it's generation process using this autoencoder. LSTM is also included here, but LSTM is not our golden hammer. We don't use LSTM when we see time division. So when we have time sequence, for example, words, and we want to create something which should follow the time rules, we usually use LSTM or GRU. So different tasks, actually prediction. So we want to base our initial node, we put our initial nodes, and we want to predict what should be next. Reconstruction task. Here you have some example. Performance RNN, polyphony RNN, Haxidria, and those architectures and demos can be found on GitHub, Medium, and you can see how this happened. Also, recurrent encoder-decoder with lookback and attention mechanism. Attention mechanism is also quite interesting because it could adjust our neural network to predict something longer. You know, I told you today that we have our data is our songs are divided into some parts. So we have intro, chorus, etc. So probably LSTM cannot hold all these things. LSTM cannot describe that we should end our intro and follow different song of part. Okay, so we have as an input we have nodes, and we are in this here you have probably GitHub. We are predicting next nodes. It's quite okay, but I will show you the results later. Autoencoder, stacked on autoencoders. So the same as in the first picture. We have autoencoder using these two visible layers and one hidden, and stacked from many layers. And of course, after training our autoencoders, we use some pseudo random input, and we put this in these hidden layers. So we are convinced that our autoencoder reconstruction task, so from this vector you want to reconstruct and get the same, we are convinced that these hidden layers are holding the whole information about music in our neural network. RBM is probably the most simple architecture to start with. It is constructed using two layers. It's restricted Boltzmann machine. And it is a neural network which have possibility to generate, which have generative possibility. And during training data, we are learning some kind of distribution. And of course, RBM has no output. There is only visible layer. So probably when you don't know how to restricted Boltzmann machine, you would ask a question: how to get the output from this neural network? The learning process is very simple. So we put our song in data representation here. We are doing training, so we have some sigmoid, V our weights, our bias, we calculate these values, and then we do the same, but this is treated as our input, and we try to put this back. So we are putting something and using the same layer visible to get this. And Gibbs sampling is used to generate. So when we use our data set, this restricted Boltzmann machine has possibility to represent some kind of distribution over our data set. And our seed, of course, is here. So we put our random vector, and we want to generate something and use this visible layer to get this. And this is also autoencoder. You see, autoencoders are very popular in generation tasks, actually. But this one is quite different because we want that this hidden layer here to follow Gaussian distribution. It's easier to manipulate this layer when we know that it follows Gaussian distribution. Yes, because we can write numpy random, we have, but when it is not random, it doesn't follow Gaussian distribution. It's we don't know what we actually want. Okay, and the different thing about learning. So in learning task, also cross entropy between these latent variables and Gaussian distribution is calculated to train something like this. And of course, the seed is here. You can imagine that when we train our neural network, we can cut all these things here, yes, and use only this element as our generator. CNN, not only font images, actually CNN is used for raw audio, so our Fourier transform can be also useful. And this is example of magenta and synth architecture. So we put our audio chunk here. We have also average pooling, and this variable z holds whole information about our raw data song. It's very big neural network, so probably when you don't have GPU, you shouldn't try to run this on your CPU, because it will explode, trust me. Seed, our seed is here. Okay, and okay, those results are from this compression. We talked about compression. So you can see that using raw audio, we can, it's original, it's reconstructed, it's quite noisy. So we should know that it happens just. Okay, probably you heard something about GANs, about generative adversarial networks, and it is StarGAN. It was published, I don't know, 3 or 2 weeks ago. It's quite impressive. So we have input our actor face. We can condition. We can add condition that as an output we want to have man with blonde hair, and our generative adversarial networks can create something like this, and it is quite nice. And generative adversarial from computer vision view, I will describe you how this works. I don't know that you probably saw this picture. So we have generator and discriminator, and these two parts are quite different. So generator is our I don't know how to say that, but he's creating something new using pseudo-noise, using Gaussian distribution. And discriminator has two inputs, and he has to show that this image, which was as an input, was fake or real. So it's quite simple. We try to generate images. We have something that is called real-world images, our data, and discriminator should recognize it was real image from our data or faked, generated. Okay, this is Minimax game. It is probably the only equation on this presentation. It is, of course, discriminator part and generator part. So we want to make generator really good. So we want the generator will create very nice images like this, yes? And discriminator should recognize that these images are faked. And GAN are also in music. So we have something like this. It's piano roll. So we put our piano roll in our conditioner CNN sheet, and this is generator using CNN, and we have convolution, we have decoder technique, and we put noise here to create something new, and also there is some kind of 1D conditions about previous steps, and we have discriminator which discriminates this song was real or not. So MIDI-net is example of GAN, and you can see this is a photo from their paper, and in advantages of their architecture they put that they use GAN, and this is their advantage over different other state-of-the-art methods. Open source code, checked. Generate multi-track music, checked. Okay, and it was a big problem for this neural network because it follows our training data. So our generated song was very similar to our real songs. So it was forced to reconstruct something from the original data set. Yes, it's a good question. So there are many tricks. It is very difficult to recognize. It was created using dataset because actually when we are predicting something, we want to generalize. But also using prediction, we want to create something pleasant. So we don't want to have random pitches of scores that are unpleasant for us. So it's a quite trade-off between these two things. So it's random generator of music, or it is training data memorizing. And there are many tricks I will show you later on next slide. So this trick was included here. So we have kind of chord conditioning in creative mode. And this is tracked from the baseline, okay? So it was trained and it follows our training data. This is the track with chords. You can see chords in second line. And this one was in creative mode, but this creative mode, as creators said, it was sometimes unpleasant because it was trade-off between originality and following the training data and overfitting. So overfitting is a big problem in all those things, but there are some results that show we can avoid this. So reinforcement learning, and it is quite nice because it uses reward as from, for example, user feedback. So you try to generate some song and you say, I don't like this, it follows our training data, or it's okay, I didn't hear that. And this could be our lost function, and this approach is very popular nowadays in this music generation techniques. So it's kind of controlling this. We are controlling the generation process using reinforcement learning. Of course, Q-learning. And as an example, RL Tuner, using it was architecture and the baseline of this system was created by Magenta Google. So we have our node RNN. Node RNN is recurrent neural network to predict next nodes. And of course, it overfits. And also it followed the rules that when one pitch was played, this pitch was played many times. So it wasn't creative. So to tune that's why it called a tuner. We use reinforcement learning, and we have some kind of music theory rules here. So we want to teach our pre-trained neural network for predicting next music pitches to follow music rules theory. And we have some kind of reward, and of course, we want to tune this, but we don't want to create something that will be chaotic. DeepHear is another architecture. It's quite big because we have two deep recurrent neural networks here. There is embedding. So, as I said, tuning our vector representation into fixed space. We have also one more neural network, merge, and one more neural network, and softmax, and we are predicting this green field here during training. So all these neural networks here, and architecture is quite big, is predicting only one green field here. Of course, it is during training. During generation process, algorithm is different. So you are doing some kind of pseudo-Gibbs sampling here, as I read here. An evaluation was conducted by humans. So you can Google it, DeepHear. If you recognize how Bach music was. If you don't, you can find this, and there you can answer some questions. So it was generated song, and it was created by Bach. And I did this short survey about results of their work, and my probability of success was 105. So I couldn't recognize it was Bach or it was generated. So it's quite nice. RNN RBM, so combining these two architectures into one. Of course, there is MIDI dataset of popular songs. What we call popular songs, we don't know because unfortunately creators of this, it was actually a blogger, Dan Schlieber. He put some MIDIs to train and validate our data, but it wasn't as popular as I thought. So basically we have our RBM units and recurrent neural network to learn long time sequences and also follow some kind of distribution. And there are more and more and more, and we can say and we can talk about this again. But it's time for tools. So I'll show you some tools which can be included in our package to start with music generation. So we have Keras, we have Music 21. It's toolkit for computer-aided musicology. So we can display some elements, create MIDI. We have some corpus data which can be used, and we have some basic rules that can be included in our neural network. We have PyMIDI and MIDI, Muse score, and Jupyter as always. And data sets for raw audio, Magnatech, Attune, and YouTube Piano. Of course, those data sets are actually piano data sets or guitar. MIDI, there are many MIDI data sets, but those data sets are from this Nottingham is probably from church. It's dataset of song from church, JSB chorals, piano MIDI, and lead sheet database, flow machine database. And I showed you at the beginning how lead sheet is constructed. And Muse data, Music XML. Music XML is also quite nice format. But it's very difficult probably to parse at the beginning. And some tricks, so don't create super AI because overfitting hurts. So you follow the training data. Start from simple architecture, so I advise you to start from RBM. Understand your data, especially in this task. Don't try to enforce, follow musical rules. You know, I show you many architectures, and probably you are disordered, but the last architecture was trying to following some kind of musical rules. So we shouldn't play this element after this because it's dissonance. It doesn't sound good. So this musical conventions and theory should be, we should add it later, after we can understand our data set. Internet scrapping, it was a nice question. Is it legal? No, probably not. So question mark about this. Genre selection, so not everybody like jazz, blues, and classical. Those data sets that I put here are from the mainly from classical music and from jazz. You know jazz. Jazz is not everybody likes this music. It's not popular. It's not repetitive. There are many features and solos, etc. It's very difficult to learn from something like this. Temperature, this is controlling the random, so we can follow some training, our training data, our distribution on, or we can trying to create something more pseudo-random. If you don't understand MIDI, use piano roll ABC notation. How to validate? You should do it yourself. So when we are trying to predict something, we can validate on another data set, yes? But when we want to validate something, we should listen to this. Those architectures, some of them are quite big, but most of them you can start using your CPU and using even mobile phone, because we was working on mobile phone application with all these things. Limits, future and conclusions. So which architecture? I don't know. You can think about reinforcement learning as our new golden hammer in this task. Adversarial training, user interaction. It's very nice idea to create tools that can generate music, but using interaction of user. So Sony Music probably is doing something similar with user interaction and generation. Overfitting versus random generator. Where is the originality? So this is also a question. Black boxing, and this is also the statement that in many neural networks and algorithms is described as we don't know what's inside. There are 20 million weights, and we want to open our black box sometimes and understand what happened. Music theorem, variable or fixed length, originality, incrementally. Will AI replace musicians? As I said, one woman created her first album or second using AI, but I think it's commercial trick to raise her popularity. So not so fast, but papers. There are many papers that was created in this week. In this week, I saw 4 new papers about music generation. So this topic is interesting for many people. And business case. Business case in this area is also really for me. It's very important because I am not only researcher, I am also developer. So I try to figure out how to sell this or make our product more better than other products. So we have key vendors of music software. Those programs are used to create music, probably also to generate. DJs, I have a friend who is DJ, and he is using many programs. Probably he know more programs than I could even imagine, and use them. And you know, when David Guetta come to the starting ceremony of I don't know, World Championship in football, he came with laptop, opened, clicked. Music for shops, games and presentations. So we can create music for shops, games, presentations. That's something that shouldn't be hit and shouldn't be as good as Led Zeppelin, for example, but it should be pleasant for our customers. Software which can help composers, so semi-AI. So it should be automatic, but users should control also what happened here. Of course, music market size is quite big, and of course, it's slice of bread for us. Okay, thank you for all these things. Thank you.